so this is pretty fun. This is your favorite part. Watch this. So the base is fun. We are limited by how much gas we can actually put out. Some people do Rubens tubes with a propane tank and a regulator, which works really well. This is fun.
Oh. It's like one of those sound boxes. Yeah. Start singing.
One more time. There we go.
So just a little. Woo!
Okay. So back to work. So that's a standing wave. And again, nodes, antinodes, pretty fun stuff.
This is a hot food.
So here's a couple standing waves. Now these are standing waves from strings. And I'm going to talk about strings a little bit. I'm going to talk about how strings are like pipes of air. This is a pipe of air. This is called a closed pipe. It's called a closed pipe because there's a solid end on one end.
Yeah.
Okay? Strings are not closed pipes. Strings are a little bit different. With a string, there's a node on either end. Okay, by the way, how many waves do you see up here?
One.
Half of one. There's one half, the other half is over here somewhere.
Yeah.
Okay, so this is half a wave. Now strings, when you have strings, they vibrate and they have nodes on either side. Our singing rod acts like a string. A little bit different though. But they have a node on either side. So here we have half a wave, one wave, wave and a half, and two waves.
That looks like pi over 2 and pi. 3 pi over 2, 2 pi.
Yeah. And they have functions which we're going to learn about in a second. We were talking, there's an equation that basically has a function of the wave and how long it needs to be to produce something. All right, so I think we talked about this before, compressions and rarefactions. So a compression is when the molecules are really close together, and a rarefaction is when the molecules have spread out. So molecules pushed together is a compression, molecules spread apart is a rarefaction. So a compression is the crest of a longitudinal wave, and a rarefaction is the trough of a longitudinal wave. So I've drawn a one wave here, transverse style, sine wave style, and this is obviously a transverse wave. But if you graph sound energy or sound pressure versus time, this is what you're going to get with a sound wave. And we're going to do that later on this week in lab. We're going to take tuning forks and we're going to strike them and we're going to hold them over microphones. And it's going to give us sine waves because it's going to look at sound pressure versus time. Now, if this is a longitudinal wave, sound pressure versus time, it's going to make this wave. Where's the crest? Where's the compression? What letter? A, B, C, D, or E is the compression? Oh, sorry, this E is actually the variable E, so, or the option E. Okay. So where's the compression?
B.
B, yeah. B is the compression. Where's the rarefaction? D, yeah. D is the rarefaction. It's not the where it passes over zero. Okay. So B is the compression. D is the rarefaction. Okay, we talked about this. Medium density determines sound speed. High density for longitudinal waves. High speed, low density, low speed. Oh, there we go. Speed in sound is 6,000 in aluminum and 960 in helium, which is kind of goofy. We'll talk about other things. Oh, temperature. There we go, temperature. Temperature also affects wave speed. So in addition to medium density, medium temperature also affects wave speed. As temperature goes up, wave speed goes up. Why? Okay, let's develop that. Why is it as a longitudinal wave travels through a medium, as temperature goes up, wave speed also goes up? Nope.
Thermal expansion.
what are the molecules doing at high temperature? Charles?
Vibrating stuff.
Yeah. Exactly. The molecules are moving faster, so they can move that medium, that wave energy, through the medium faster. So in addition to density, how close the molecules are, the medium's temperature also plays a role. The faster moving molecules will move the wave energy through the material faster. Higher temp, faster, faster wave. How are we doing? We've got about 5 minutes left. Good? Give me a thumbs up if you're ready, if you're good, ready to move on. Oh, you're taking a picture? Okay. That's how they do it, like the Asian girl picture. All right, here we go. Is the speed of sound greater in Las Vegas or in San Francisco at sea level?
Las Vegas.
Las Vegas.
It's
hotter.
Sea level. It
But
would
it's
be-
hotter in Vegas.
It also is colder in the winter, so
What?
In general, the speed of
it
sound
would be at
is
sea level.
at greater at sea level. Yeah, greater at sea level. Because there's more pressure.
Yeah.
Molecules are closer together.
More breathing air.
More breathing the air. So more pressure, molecules are closer together. The speed of sound is greater at lower altitudes. At higher altitudes, it's less. So when you're driving, when you're flying along, and the captain comes over the intercom and says,
Oh, ladies and gentlemen, we're going to make up some time. We're doing about 650 miles per hour, which is great at 15,000 feet. We're going to rack it up to 45,000 feet and travel at the same speed.
be afraid. Because as you go up in altitude, the speed of sound actually drops to the point where you could travel the same speed and ascend and break the sound barrier. Why is that a problem? We'll talk about why that's a problem a little bit. Okay, so 30,000 feet, less. Okay, less. What is the frequency of a wave with a speed of 340 meters per second and a wavelength of 1.4 meters? So we can do this, right? Remember, what's the equation for the speed of sound? Or sorry, speed of a wave? Wave speed equals, yeah, frequency times wavelength. So speed is meters per second, and wavelength has a unit of meters, and frequency has a unit of per second. So wavelength is frequency, or wavelength times frequency gives you speed. So, what's the frequency?
2.3 hertz.
Probably something along those lines. Alexa, what's 340 divided by 1.4?
240 divided by 1.4 is 242.8571.
243. So you saw a big explosion. You're like,
do be smart.
you're outside, you hear this boom, big explosion. Someone set off some dynamite. There's a mining charge over there. Do you see it or do you hear it first?
You see it.
You see it. You see it first. But then do you feel it or do you hear it first? You feel it. So first you're going to see it, because light travels faster in general. Then you're going to feel it in the ground, because it travels faster than the ground. Then you're going to hear it in the air. Okay, this is a good place to end, all right? Sound pressure. So sound pressure or energy is measured in decibels. Deci, literally, tenths of bells. Alexander Graham Bell, all right? So sound intensity is given the unit watt per square meter. Watt is energy divided by time. Remember work? So work is joules and power is watts. Energy divided by time is watts. So it's basically watts per square meter is wave intensity, wave energy. And the decibel scale works like this. Every 10 you go up on the decibel scale, you have 10 times more wave energy. Make sense?
Yes.
Does that mean 100 decibels means 100 times more energy? No. It means if you go up from 80 to 100, you have 100 times more wave energy. Every 10, you multiply your wave energy by 10. So from 30 to 40, 10 times more energy. From 30 to 50, 100 times more wave energy. From 30 to 60, 1,000 times more wave energy. And from 30 to 70, 10,000 times more wave energy. So if you're like, Yeah, 100's not so bad. 110, 10 times more energy. By going by a step of 10, 10 times more
So the
energy.
exponent is
Logarithmic. Yeah, it's a logarithmic sound scale. It's a logarithmic sound scale for reasons that no one knows. Instead of going 1, 2, 3, 4, which would make sense, like the Richter scale, they go 1, 2, 3. We had an earthquake that was 6.9. Okay, an earthquake that is 7.0 has 10 times more energy than 6.0. It's a true logarithmic scale. Somewhere along the line, somebody said, I don't want to use decimals. I just want to say 65 instead of 6.5. Decibels. It's a logarithmic scale, but they slap a 10 on the end of it for reasons that I was never informed. Okay. Lastly, last 2 minutes of class. Yeah.
So what's the lowest sound you can hear?
Frequency. We haven't talked about frequency, but frequency, the lowest you can hear is about 30 to 40 hertz,
30.
depending on your age. And the highest you can hear is between 10 and 20,000 hertz, depending on your age. We'll talk about that later. Okay. So last thing, sound intensity. I'm basically going to end here and pick it up tomorrow the same way. Sound intensity falls off with the square of distance. The waves that go out in every direction go out in 3 dimensions. If you measure something in a single dimension, something that goes out in 3 dimensions, it will fall off with those other 2 dimensions. So if you look at the sound at 1 meter and the sound at 2 meters, then the sound at 3 meters, by doubling the sound different, by going from 1 meter to 2 meters, by doubling the sound distance, you will fourth the sound intensity. Okay, so we'll stop here, pick it up tomorrow.